This is 11-3. Next couple are going to help us deal with the impulse momentum theorem. So here we have two disks, A and B, initially at rest on the left end of the track. Disk A is more massive than disk B. The track has a horizontal section and then curves upward at the right. The disks are simultaneously pushed to the right by identical, constant horizontal force of magnitude F for the same amount of time. The forces are removed before the disks reach the curved section of the track, and there's negligible friction between the track and the disks. So what I'm thinking is that they both have the same force, both have the same time. F delta t is equal to impulse, which is equal to the change in momentum, and that is in fact where this problem is going. Part A says the graph above shows the velocity of each disk as a function of time, while the disks are moving on the horizontal section. Identify which disk's motion is represented by the solid line. Okay, so what's happening to the velocity here? Velocity for each disk is increasing, but the velocity of the solid line is increasing more. Remember, the slope of the velocity versus time graph is acceleration. So we can tell that the solid line is accelerating more. So back to the two disks, they both have the same force. Okay. The mass of disk A is larger, so the acceleration of disk A must be smaller. So that tells us that the solid line then is disk B. Okay, so 3 points for part A, 1 point for saying disk B, 1 point for indicating that the slope of the velocity versus time graph is the acceleration. That's a unit 1 concept. And then 1 point for saying the smaller mass will have the greater acceleration due to the constant force. And that's our unit 2 question, all up in one little package there. So 3 points for part A. Part B, when the horizontal forces are removed, which disk, if either, has a greater momentum? If they have equal momentum, state this explicitly and justify your answer in terms of the impulse acting on each disk. So they actually give you a hint to that one, right? If you weren't thinking of impulse before, you are now because you just read the word, right? Well, what's impulse equal to? Force times the time that it's applied. If you go back and read the introduction again, you find that the forces are the same and the times are the same. So they equal the same, they experience the same impulse. Then we have to remember that impulse is equal to a change in momentum, and both started with 0. So at the end of this delta t, they will have the same final momentum. Okay, so I wrote they both experience the same impulse, F delta t, because they say, talk about this in terms of the impulse. Since F and delta t are equal for each situation, since the impulse is equal to a change in momentum, since each had an initial 0 momentum, then the momentum is the same after this force is applied. So you just get 1 point for part B. 1 point for saying that they have the same impulse, but your justification better implicates something about momentum, or else I don't think you'll get that point even then. All right, C and D are basically C is the answer and then D is justifying it in a paragraph, so we'll do these together. After sliding across the horizontal section of the track, both disks slide partway up the curved section of track. Identify which disk, if either, reaches a maximum height. If both reach the same height, state this explicitly. Okay, so the answer is here that disk B is going to go higher, right? Since both disks have equal momentum, okay, we decided that both disks have equal momentum. The disk with the lower mass has the higher kinetic energy. And we've done this before. If we have for disk A and disk B here, disk A has a high mass, which means it has a low speed. Disk B has a low mass, which means it has a high speed, but this is a linear proportionality. If the mass is twice as big, the velocity is half as big, etc. Then when we head over to our kinetic energy formula here, right, this favors the object with the lower mass and the higher velocity because the velocity is squared. Now, we've had that conversation before. If you're still unsure, let me know and we'll have it again. So that tells us that disk B has greater kinetic energy, right? And what does this ramp do? It essentially uses Earth's gravitational field, converts kinetic energy to gravitational potential energy. Okay, so the disk with the greater kinetic energy is going to have the greater gravitational potential energy. And since the mass term cancels out here, right, 1/2 mv squared at the bottom, mgh at the top, it doesn't matter that disk A has a higher mass, the mass cancels out. So disk B is going to go higher. So how does the rubric go there? We get 1 point for saying disk B goes higher, 1 point for using conservation of energy, 1 point for saying that the disk with the greater kinetic energy will have the greater final gravitational potential energy, 1 point for indicating that the mass terms cancel and don't affect the height, 1 point for saying that the disk with the greater gravitational potential energy goes higher. That is somehow indicating that the gravitational potential energy is mgh, and then 1 point for the logical relevant argument. So 1, 2, 3, 4, 5, 6 points for that paragraph. I think, honestly, this was part C, 1 point for part C, and then the other points for the paragraph. But it doesn't matter how you grade that. 6 points total for C and D. And that's number 3.